Hey guys, welcome to MACM 101 Discrete Mathematics Tutorial 1. My name is Inderpartap and I am one of the TAs for this term and also the host for this tutorial today. Each week we will be posting pre-recorded tutorial videos over the weekend, and in addition to that we will host live Q&A sessions every Thursday. Now, we haven't yet decided on the timings, and we will adjust those for the sessions based on the class participation. But for the next week's tutorials, your timings are posted on the Canvas homepage. Now, in these videos, we will provide step-by-step explanation for every single question, but you are encouraged to try and solve these on your own before watching the videos. There could be more than one way to solve a problem, and what we provide is just a guide. We are not going to restrict on how you solve these questions. Now, that's all I had for the introductions. I hope you enjoy this course. Thank you. In this week's tutorial, we are covering propositional logic and laws of logic. And we have 8 problems which are fairly simple in nature. So let's dig into them. The first question is state the converse, contrapositive, and inverse of each of these implications. Now, when you are asked to play with implications, you need to find a hypothesis and a conclusion. So, in this, uh, let's say you have a conditional statement P implies Q, or equivalently, if P, then Q. So your hypothesis is P and your conclusion is Q, because if P happens, then Q will occur. So for this conditional statement, your converse is when you interchange two statements. So from P implies Q, it becomes Q implies P. Your contrapositive is you negate both the statements and then interchange them. So it becomes not Q implies not P. And similarly, your inverse becomes uh, it's just the negation of both the statements. So it is not P implies not Q. Now, the first part is if it snows today, I will ski tomorrow. Snows today is your P, and ski tomorrow is your Q. So for converse, we just switch them up and it becomes if I will ski tomorrow, it snows today. We are doing nothing but finding the hypothesis and the conclusion and then reversing them up. And that gives you your converse. For the contrapositive, we take the inverse and then we negate the P and Q. It will be if I will not ski tomorrow, it does not snow today. And for the inverse, we are just taking the negation of both the statements. That will give you if not P, then not Q. So it is if it does not snow today, then I will not ski tomorrow. For the second part, it is I come to class whenever there is going to be a quiz. Again, the converse is pretty simple. You just switch them up. It will say there is going to be a quiz whenever I come to the class. Or you could also switch it in a way where it reads if there is going to be a quiz, then I come to a class. That's another way of representing this statement, but it's up to you what you follow. So here we are just going with what the statement reads. The converse becomes there is going to be a quiz whenever I come to the class. For the contrapositive, again, we are switching and then negating them. It reads, there is not going to be a quiz whenever I don't come to the class. And for inverse, again, it's just the negation of both the statements, and it would be I do not come to the class whenever there is not going to be a quiz. For the third part, now this might get a little bit confusing for you guys. It says a positive integer is a prime only if it has no divisors other than 1 and itself. Now, uh, from Kenneth and Rosen's discrete mathematics, uh, P implies Q can be expressed as P only if Q. So here, this only if represents an implication. So positive integer is prime, is your hypothesis, and the other part is your conclusion. So now the converse becomes a positive integer has no divisors other than 1 in itself only if it's a prime. So we just switched the conclusion and the hypothesis. For the contrapositive, we will write a positive integer has divisors other than 1 and itself only if it is not a prime. For the inverse, you take the negation and it will become a positive integer is not a prime only if it has divisors other than 1 in itself. Now, moving to the second problem, it says express these system specifications using propositional logic, construct the truth table for the compound statement. Access is granted whenever the user has paid the subscription fee and enters a valid password. So, only when you pay the subscription fee and you enter the valid password, you will get the access. So, if you say subscription fee as P and entering the valid password as Q and access being granted as R, so it becomes P and Q implies R. So before we write, let's look at the truth table for P and Q. It's 1 only when P and Q are both 1, otherwise it's 0. And for P implies Q, it's 1 when Q is 1, we don't care about P, and 1 when both P and Q are 0. And when P is 1 and Q is 0, it's 0. Now, taking that into consideration, let's draw our whole truth table for P, Q, and R. P and Q is 1 only when both P and Q are 1, otherwise it's all 0. And for P and Q implies R, first we check where R was 1, that's 1. And when both P and Q and R were 0, that's again 1. And it leaves us with only one column where it's 0. And that's your whole truth table. Moving over to the next problem, we are asked, are these system specifications consistent? The first line is the system is in multi-user state if and only if it is operating normally. So if and only if is a biconditional, which means m biconditional n. The second line is if the system is operating normally, the kernel is functioning. So if, then the conclusion. So n implies k. Third line is the kernel is not functioning or the system is in an interrupt mode. So not k or I. Fourth line is if the system is not in multi-user state, then it is in interrupt mode. So if not m, then I. And the last line is the system is not in interrupt mode, which means not I. Now to solve this, we'll combine all these expressions and try to come up to a tautology or a contradiction. Let's start with the most simplistic one, which is not I. That just means I is false. The second one, which uses this, is not K or I. So for this to be true, since we know I is false, so K, not K must be true, which means K is false. The third one is not M implies I. Now, since we know I is false, so for the whole statement to be true, the left side or the hypothesis also needs to be false. So not M is false because false implies false is how we make it to be true. Now, since not M is false, M has to be true. And the next statement which we use would be M biconditional N. And that is M is true if and only if N is true. And since we know M is true, that means N is true as well. And the last one which uses N is N implies K. Since we already know N is true, for the whole statement to be true, K has to be true as well. So K must be true. But this brings us to a contradiction because we had K to be false in the second step. And that's why these system specifications, whatever we were provided with, they are not consistent. Moving over to the fourth problem, we have construct the truth tables for each of the following formulas. P implies Q implies Q implies P. So we'll start off with first solving P implies Q. We know it's 1 when Q is 1 and when both P and Q are 0. Then we'll solve for Q implies P, which is 1, 0, 1, 1. And then for the whole thing, again, when Q implies P is 1, it's 1. And it's 0 when the proposition is 1 and the conclusion is 0. For the second part, we have P biconditional Q XOR not P biconditional Q. So the biconditional is true only when they are both the statements are either 1 or 0, and it's 0 otherwise. So we'll solve for P biconditional Q and not P biconditional Q. And for the XOR, it's 1 only when either of the statements is 1. And if they are both 1 or both 0, it's 0. And that gives us our solution. For the third part, we have P implies Q and not of P implies Q. So for P implies Q, we know It's 1 when Q is 1, and when both P and Q are 0, it's again 1. For not P implies Q, I seem to have made a mistake. It should be 0, 1, 1, 1. And for P implies Q and not P implies Q, it's a simple and of these two statements. It's 1 when they are both 1, and otherwise it's 0. Let's move on to question 5. It says there are two tribes living on the island of knights and knaves, and they are knights and knaves. Knights always tell the truth, and knaves always lie. You encounter two people, A and B. What are A and B if A says B is a knight and B says two of us are opposite types? So let's start by assuming A is a knight, and since his story is true, that means B is a knight. And now B said the two of us are opposite types. And since B should be a knight, this statement should be true, but it's a contradiction. That means our initial assumption was wrong. So A is a knave. And since A is a knave, uh, B is a knight statement is also false. That means B is a knave. Now, to verify this, we can see B says two of us are opposite types, and since this is false, they are both the same type, and that's true. So for sixth question, again, we are on the island of knights and knaves. Now, the statement changes a little. A says the two of us are both knights, and B says A is a knave. Again, we will start with an assumption and see what do we come up to. So, assuming A is a knight, the statement two of us are both knights is true, which implies B is a knight as well. And since B is a knight, B's statement should also be true, which is A is a knave. That is a contradiction right there. So we change our assumption. We'll start off again, and let's assume B is a knight. So if B is a knight, B says A is a knave, and what A said was the two of us are both knights, and since it's a lie, it should mean that they both are not knights. So either one of them could be a knave, which is fairly true with our statement. So A is a knave and B is a knight. That's the solution to our problem. Moving over to the next question, we have use truth tables to verify absorption law. Now, absorption law can be written in two ways. One is P and P or Q biconditional P, and the other one is P or P and Q biconditional P. So for the first one, we start off with P or Q. It's 1 when either of P or Q is 1, and 0 when they are both 0. And you AND it with P, you get 0, 0, 1, 1. Here you can see P and the final statement, their truth table look completely identical, and that's why they are the same. Moving over to the next problem, P and Q, it's 1 only when both P and Q are 1, and when you OR it with P, it's again the same. Again, the truth tables match for P and the other thing. That's why they are both the same. For question 8, we have show that P implies Q and Q implies R implies P implies R is a tautology. Now you can show this with a truth table, but here we are to use equivalences. So here we'll start off with the implication law, which is will decompose of all the implications. Uh, so A implies B, it can be written as not A or B. So here we uh, write up all the implications, which is not of not P or Q, and Q implies R is written as not Q or R, or and P implies R is written as not P or R. Now we use the De Morgan's law to take up the negation sign inside the brackets, and when we do that, we switch all ands as ors. So it becomes not of not P or Q, or not of not Q or R, or not P or R. We use this De Morgan's law again, and we take up the negations even further down into the brackets. It becomes not of not P and not Q, or not of not Q and not R, or not P or R. Now we just use the commutative law to rearrange this sentence. It can be rewritten as not P or not of not P and not Q, or not of not Q and not R, or R. Now with this, we can use the distributive law to take these not P and the R into the brackets. So using distributive law, it would give me not P or not of not P, and not P or not Q. So this was one usage of distributive law, and now we use it again with the R. So that would give me R not of not Q or R, and not R or R. So here we just use the negation law and the definition of tautology. So your first part, not of not P, becomes P, and P or not P is the definition of tautology, and this can be rewritten as T. So tautology and not P or not Q, or the second half remains the same. It's Q or R, and not R or R is again the definition of tautology. It can be written as T. And now using the identity law, so identity law states P and T is the same thing as P. So here it reduces as not P or not Q, or Q or R. And then we use the associative law to rearrange it again. And not Q or Q is again using tautology, it becomes T, and your whole statement through domination law becomes a tautology. And that's it. That's all we had for tutorial 1. I hope to see you guys in the Q&A sessions. Have a good weekend everyone.